Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends. I'm a theoretical physicist currently doing a postdoc in the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, basically all of the cool stuff happening inside the universe. It's a great topic. I love being a cosmologist. I love that I get to work on trying to figure out what the universe is made of and what's happening up there. And I love chatting to everybody about all of the cool things I get to research. So for anybody who doesn't yet know, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want about physics, about cosmology, about academia, about space, about myself, which I may not answer, but you're welcome to ask. You can ask me anything you want, and I will do my best to answer your questions. So this means that you have complete say over what we talk about. There is no planned topic today. This stream will go in whatever direction you all want it to go into, and whichever direction I feel like talking about, because that's usually what happens. I find the fun tangents to run down. So hello to all of the regulars joining. I see we have Ange, we have David Howden, we have James, we have David Dunn, two of the Davids in already. We have Ben, we have Prath. Welcome everybody. Great to see you here. For any first-time viewers, welcome. If you haven't done so yet, please do leave a comment, like the video, subscribe, press all of the usual things, make stuff happen, press buttons. You know, pressing buttons is fun. Press all of the buttons on YouTube and see what happens. Please don't press the down vote button. Press all the other buttons and see what happens. Press you did not miss anything. You were 2 minutes in. I'm just doing my usual introduction. Don't worry, you have not missed much yet. And as always, if you do miss stuff, you can watch the replays. The replays are always up and you can always go back and watch them. So yes, this is an interactive stream. The idea here is that you can ask me anything you want and we will take it from there. Currently, just to give you an idea, I am working on gravitational waves. Gravitational waves are these ripples in the fabric of space-time caused by basically anything moving through space-time. And they are tiny, tiny vibrations in the background of the cosmos, which is amazing when we think about it. And that is what I get to work on, which is super cool. Other things I've worked on include dark matter, which is one of the weird types of matter that holds the universe together. We know that the universe has three main components: everything you see, everything you're accustomed to, everything from me to the stars you see at night, everything in between. That is normal matter. Normal matter is only about 5% of the energy budget of the observable universe. There's another big chunk, about 26%, which is in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally but doesn't interact electromagnetically. So dark matter pulls stuff together, but light does not see dark matter. As far as light is concerned, dark matter is not there, which makes it very difficult to study when it is invisible. Then there is the remaining 69%, which is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that is pretty much everything we know about dark energy. How do we know these things? Well, we have amazing observations of the universe, including everybody's favorite, the cosmic microwave background radiation. This is the oldest light we can see in the universe. This is the afterglow of the Big Bang itself. By looking at the orange and blue spots here, we can figure out what the universe is made of. So by getting this map here, we can figure out this pie chart here. So we use that map to figure out what the universe is made of. This is just a quick fire introduction to the types of things I've worked on, just to set the scene, just to give you some questions. But as always, you can ask me anything. And yes, that absolutely was an excuse to flash the CMB within the first 3 minutes of the talk. Okay, let's catch up with comments already. I see Prathya saying you had the worst FOMO of all time this weekend with the Auroras. Yeah, if it makes you feel any better, I did not see any in Helsinki. You know, up north, we're supposed to see northern lights. And one of the reasons is there was a lot of solar activity this weekend. If you got to see the northern lights, it's amazing. I personally didn't get to see it. Currently, there's the other thing that I found quite annoying, that it gets dark really late. I know people like the long evenings. I am a winter dark vampire person. And right now the sun sets at like 11:30 or 11 o'clock in Finland. So it doesn't get properly dark until after midnight. So if you want to see northern lights in Finland right now, there's like a 4-hour window where it's dark enough to actually see them. And I'm not up that late usually. I'm not sure if people did see them in Helsinki. I know in the surrounding areas where there's a bit less light pollution, there were a lot of northern lights, but I did not see them in Helsinki. So for those of you getting FOMO because you didn't see it, don't worry, I didn't either. And I'm technically in the place where you're supposed to see them. I have seen them twice now in Helsinki, which is very, very cool because normally you have to go outside the cities to see them. I have seen them twice in Helsinki, but I didn't see them this weekend. But I completely get the FOMO if you wanted to see them and didn't. But don't worry, the sun is currently increasing in activity. The sun has an 11-year cycle, during which, when it's at its peak, there are more solar flares, and therefore there are more higher chances of catching northern lights. So if you didn't catch them this weekend, don't worry. There's likely to be quite a few in the next year or so. So there might be other chances of seeing them. But I completely get the FOMO of not having seen it, because it was, from what I've heard, very spectacular. We did not have them here, or at least I did not see them. I wasn't. I had a notification on my phone this morning when I woke up at like 2 o'clock in the morning, like, go out to look at northern lights. Like, no, sorry, I'm not. I'm not up at 2 o'clock. I am not that young anymore. I don't stay up like until 2 o'clock on a Saturday night. I was in bed. So, yes. See comment here from David Howden. You managed to miss them too, partly because I was just too tired and failed to wake up. Yeah, I get that. Moth trapping and conference. Yeah, I honestly, sleeping is good. Sleeping is good for you. And Northern Lights are amazing, but if it's a choice between Northern Lights and sleep, last night at least I chose sleep, which was a smart choice in my case. But yes, there should be more of them coming this year. This year there's going to be probably a lot of solar activity. Of course, it's always easier to see them in the darker months. It's a big problem in Finland that now there's just too much light. So then, yes, it is hard to see them right now here. You saw them in North Carolina on Friday. Yeah, apparently they got pretty low. People saw them in Germany as well. So yeah, they've definitely been going quite far south this time. And I see a lot of people here talking about whether you've seen it or haven't seen it. But yeah, it's very cool if you do get to see it. Northern Lights are a very pretty thing. And it's one of those things that I think understanding the physics of it doesn't make it any less magical. Right? I can explain how northern lights work. There's just charged particles caught in the magnetic field of the Earth. It doesn't make it any less magical. And this is something that I love about science. That sometimes people are like, oh, science takes the fun out of things. No, I understand what a northern light is. I understand how auroras happen. And I still think they're incredibly magical. I also think rainbows are magical, and I also know how those work. So I think the science is magical and amazing, and the fact that we get northern lights, that we live on a planet, that we have this atmosphere that has a magnetic field that protects us from these solar flares, but also diverts them, and makes these pretty light shows for us. I mean, that is kind of cool. That is kind of cool. So it's very cool that we get to see these. Southern lights are a thing too, right? Yes. You can get the Aurora Australis as well, apart from the Aurora Borealis, which is in the north. You can get the Aurora Australis, because you imagine this is the Earth, here's my sphere, this is the Earth, this is the sun, it sends us charged particles. These charged particles get caught in the magnetic field of the Earth, so they get diverted to the North and South Pole. And as they fall down these magnetic lines, that is where you get the Northern Lights, or the Southern Lights. So Southern Lights are also possible, but there's just fewer people living in that region where you would see them. So it's usually much more likely to get them in the north. But yes, you can also get Aurora Australis, which is also hard to pronounce, at least for me. Question here from Prath. I know there's a question here that I just missed from James. We'll get back to that in one sec. But staying on the topic of the auroras, question from Prathia. I know Earth and Saturn get aurora. Which other planets do? I think Jupiter does as well. And I'm not sure about the other planets. You require a magnetic field, and I'm not sure if the magnetic field in Jupiter is strong enough for northern lights. Saturn definitely gets them. I'm not sure which other planets do. I'd have to check that, but it's cool. But yes, Saturn does get them as well, which is very, very cool. Jupiter does. David Dunn here saying Jupiter does. JWST saw them. That is true, actually. Yes. I seem to remember there was that thing that's one of the things JWST saw in one of its first images. There was this picture of Jupiter where there was like the glowing band at the top and at the bottom. Yes. Mars is probably not getting them, because Mars does not have that kind of atmosphere anymore. It might have done it in the past, but it doesn't anymore. I wonder, I might actually have the photo at hand of Jupiter and the Northern Lights, but it is somewhere in my stack of 47 images, and I do not remember which image it is, if it's even still in the slide deck. So I am, in the background while I'm chatting, I'm just flicking through my slides, looking to see if I have the one of Jupiter with the Northern Lights. It might be here somewhere. It's not within the first 21, but it might be here somewhere. Okay, that looks like a JWST. Okay, here we go. This is one of the images that JWST took of Jupiter. This was one of the ones released, I believe, in one of the first data releases, so it was quite an early one for JWST. This is Jupiter. You can see the great red spots, and you can see these kind of glows at the north and the south. So yes, this is very much one of the very cool images that JWST took of Jupiter. And if you're wondering why the colors look different to how we normally see Jupiter, it's because this is in infrared, so it's slightly shifted. So everything looks slightly off. But yes, this is Jupiter as seen by JWST. It's a very cool photo. It's very cool that we get to see Jupiter like this. But yes, I knew this image was somewhere on my slide deck, so for future reference, this is slide 22, which does not help me because I do change the slides around like every few weeks. I'm like, wait, this order makes no sense, and then I move things around, and then I can never find things. Why is the great red spot shining so bright? I'm actually not sure. I think it's just something that shines brighter at the infrared frequencies because of the way the storm is gathered there, but I'm not sure. This is a question maybe more for David Dunn on David's show, because planets are quite small compared to the whole universe, and planets are the things that we just say like that's a point. We leave that to the people who study planets. So it's not something I'm by any means an expert in, but I would say the red spot looks brighter in infrared because it's just the wavelengths that dominate there. So might be related to the storm. I'm not completely sure. And this was the first time the aurora was seen in infrared. That is true. Hubble had seen it in ultraviolet before. JWST was the first one to see it in infrared because they're looking at slightly different regions of the electromagnetic frequency, of the electromagnetic spectrum. They're looking at slightly different regions. So that's why we usually with Hubble, we were getting more in ultraviolets, but now with JWST, we shift more towards infrared. Yes. You're unusually highly soaked in beer tonight. I mean, good for you. Enjoy. Might make this show more entertaining. I know at some point someone mentioned a drinking game with my show. If you're doing that, just please be careful, drink safely, do your thing. Drinking game, drink every time I show the CMB would be a terrible idea. I do not endorse this, but you do you. And if you all want to start a drinking game in this show, I'm not going to stop you. Just let me know, because then if I know, then I can play into it. Okay, yes. There were more comments here, just saying on the topic of auroras. I know there's the other question to go back to in a minute, but staying on this topic, question from David Howden here. Does the color of the aurora tell you anything about the atmosphere of planets that have them? That is an excellent question. I have no idea. I feel like it might. It should, right? Because I'm just thinking on the spot here, when the charged particles get caught in the atmosphere, the reason we see them glowing is because they're charged particles crossing the atmosphere. So could we use that to figure out the atmosphere? I have no idea. I think that's a very cool question, and it's one that I could see that being a possibility. I'm not sure to which point that's something we can do. But yes, why the color of northern lights? Maybe not, actually. I think it might just be related to the particles that the sun is emitting itself, because here we get northern lights ranging from like purple to green, and it kind of covers quite a range. So it's not necessarily related to the composition of the atmosphere so much as the amount of particles that we're getting, maybe. I think that's a very cool question, David, and I'm actually not completely sure. But yes, a comment here from David Dunn saying oxygen and nitrogen show colors in our atmosphere. That sounds very believable. I'll believe that. So yes, it might be related to the composition. I'm not sure if then you could use northern lights or auroras on other planets to figure out the composition. I guess if we're at the stage where we can actually measure northern auroras on other planets, we've probably already got a pretty good understanding of that atmosphere, because if we are able to take that type of photos, we're probably also able to do some type of spectroscopy and figure out what the atmosphere is made of. So I feel like if we're close enough to actually measure the auroras, we can probably do other techniques to figure out what the atmosphere is made of. But it would make sense that the colors determine the atmosphere. This gives me so many ideas. This is something that annoys me a bit about sci-fi writers, that often the planets you get are so Earth-like. But you could have planets with random atmospheres where you have northern lights that shine, I don't know, bright orange or something. And this is an element you could play with. You could have planets with different colored skies. Instead, we always get the default blue or maybe orange if they're feeling fancy. It would be so cool to see actually sci-fi actually exploiting the different possibilities there. But this is absolutely a tangent here. The different colors are from different gases. Yes, green is oxygen. That sounds reasonable. Nitrogen is slightly, nitrogen should be maybe more purple. I'm not sure, but yes, it is. It is very, very cool. But yes, it does make sense that the northern lights or the auroras change the term depending on the atmosphere. So that is a very cool question. I love that question. And we just have the comment here that the Great Red Spot is indeed reflecting in infrared more than the rest of Jupiter. So that's why it's shining brighter there. Okay, let's see. Going back, there were some very cool questions here about northern lights. Let's see if I got them all. I really like that question of northern lights and the colors. I think that's very, very cool. Okay, planets with different gravity. Yeah, you could have so much fun with sci-fi. Like going, there's so much you could do, and instead we always get human-like or humanoid-like bipedal aliens with some semblance of communication and living on a planet that is very Earth-like. It's like, come on, give us more. You can do anything you want, especially in the realm of sci-fi. Why are all the planets boring? Why does everyone in Stargate speak English? This is still a pet peeve of mine. I love the show, but Also, I'm currently, if you're wondering why I'm on a sci-fi tangent, it's because I watched the new episodes of Doctor Who this afternoon and I'm hyped. I'm hyped. I love them. Keeping it completely spoiler-free, but I'm hyped. I love the episodes. Okay, back on topic. Or not that we're on topic, but back on topic. All alien planets look like Aquarian whales. They do, don't they? All alien planets look suspiciously like Aquaria. Yes, though that is. I appreciate the Doctor Who reference there, David. Very nice. Okay, on to questions. Moving on. There was a question that I wanted to answer some time ago. Where was it? Just seeing a comment here. You're planning to drive to Alaska and feature as an excuse for Northern Lights. Excellent plan. Very much encourage that. Driving through Alaska is supposed to be incredible. Very much encourage doing that. Okay, where was the question that I wanted to answer? There was a question here from James. Basic question, there's no such thing. All questions are cool. Do we know the age of the universe? And if so, we must know how big the universe is, including the universe that is no longer observable. Love that question. That is a very cool question. The answer is yes, we do know how old the universe is. The universe is 13.82 billion years old. We know this thanks to measurements of, for an example, the cosmic microwave background radiation. By measuring the CMB, the cosmic microwave background radiation, one of the numbers that we can pull out from this is the age of the universe, assuming a cosmological model. Once you have the CMB, you get your parameters for your standard cosmological model, which in our case is lambda CDM, where the universe has dark energy and dark matter. You use that cosmological model and the data from the CMB to calculate the age of the universe. So the universe is 13.82 billion years old. This also means we can figure out how big the observable universe is, because we know that light travels at a finite speed. Nothing can travel faster than light in a vacuum. With this, we can calculate the theoretical maximum distance that light has been able to travel in the age of the universe. And this gives us the idea of the patch of the universe that hypothetically could send us information. And this is what we call the observable universe. The observable universe is a bubble centered around us, because we're talking about light that could have reached us. So the observable universe is a bubble centered around us, and it has a radius of about what is that number? Why do I always go for radius when then I can't divide in my head? About 47 billion light years. That is the radius of the observable universe. If you're wondering, how do we get 47 billion light years when the universe is only 13.82 billion years old? That's because the universe is undergoing accelerated expansion. The universe is expanding. So the light that could reach us today could be much further away now. So if a galaxy is sending us light, by the time the light reaches us, that galaxy is further away than it was when it sent that light. So then we can see things that are further away than what we expected them to be. So the observable universe has this radius of about 47 billion light years. And we know this based on the age of the universe. Now, your question of can we use that to figure out the size of the entire universe beyond the observable? We cannot, because to do that, you would assume that the universe starts as a small dot and that everything then grew inside the universe. But that is not the case. The universe was infinite before, it is infinite now. So the size of the entirety of the universe is quite hard to measure or to quantify because the universe is everything in existence. And once you put a size on it, you're putting borders, and that means you're talking about an inside and an outside. But what would the outside of the universe be when we said that the universe is everything in existence? I realize I left the CMB up here. Not intentional, it's just, there's a CMB on the screen, might as well just leave it there. That was not intentional. That should have gone away a few seconds, a minute ago or so. So yeah, we have the observable universe, which is this bubble around us, and we can use the age of the universe to get an idea of the size of the observable universe. But we can't then extrapolate that to the size of the entire universe, because the entire universe is infinitely big. It was infinitely big after the end of inflation. It is infinitely big now. It is a bigger infinity. But, other than saying it's bigger than infinity, but it's still infinite, it's quite hard to give it any resemblance of number or quantity, because then we're talking about size, and the size of the entire universe is something we cannot know. But we can measure the size of the observable universe by using the age of the universe and the fact that light travels at a finite speed. My hair is all over the place today. I have this patch here. If you wonder why I keep doing that, it's because hair is all over the place. Yes, I do have hairpins. No, I'm not going to wear a hairpin. Anyway, just going to be fidgeting all day because hair's in the wrong place. But that's fine. Neutron star dwellers in Dragon's Egg were quite different to humans. That is cool. I have not seen or read Dragon's Egg. I'm going to make a note of that. Dragon's Egg. That sounds cool. Thank you for the recommendation. I know it was not a recommendation, but that sounds cool. Dragon's Egg. That sounds dramatic. I love things like Dragon's Egg. In Dragon's Egg, didn't generations pass just during the astronauts' attempts at communicating with them because of time dilation? That would make sense. That sounds realistic. I'm starting to like the idea of this program or book or whatever it is. This sounds cool. I'm going to check that out. Okay, back to, there were some other questions that I wanted to get to. I'm going to just take this from the top and check all of the questions to see that I got to everyone, or make sure that I get to everyone. Take advantage of the fact that my tea is currently almost perfect temperature. Okay, so we talked about northern lights, we talked about southern lights, we talked about which planets have auroras, which is a word that I do struggle to pronounce, as you might have noticed. We talked about the colors of the auroras. That was such a cool question. I love that question. Okay, comment from Scott here. Going back a bit, we would get solar eclipses every month if it wasn't for the orbital inclination of the moon, right? Earth's axial tilt just causes the sine wave-like path. So it's not so much, is it related to the Earth's tilt, or is it related to the fact that the moon doesn't lie on the same plane as the sun does? So the sun and the Earth, you can consider them to be on one plane. That is like the galactic plane. We're actually like slightly shifted from the galactic plane. So if this is the galactic plane, this is the solar system. But let's consider the plane of the solar system. So you have the sun doing its thing, you have Earth doing its thing, 7 degrees tilted. So is the moon locked? Yeah, so the plane between the Earth and the moon is not parallel. It's not exactly the same. If this is the plane, you have sun here, Earth here, this is the line between them. If they're both spinning like that, you can draw a line between them. This is like the center on which they're rotating. On the Earth-Moon plane is slightly tilted, and therefore you don't get the moon always going through the passage. Otherwise, we would indeed, if they were on exactly the same plane, then you would indeed get an eclipse every month, because the moon would always go between the Earth and the sun every month. The fact that they are slightly tilted means you don't get eclipses every month. But yes, they are different planes of rotation. Also, if you think this is the galaxy, the solar system is rotating in that plane, and then inside that you have the sun-moon system at a different plane. So there's a lot of different planes of reference to consider, which is very fun. I hope that answers your question, Scott. Not sure if it does, but hope that answers your question. If not, as always, let me know. If anything I say is not clear, ask me again, and I will try to answer another time. Just going to check if there's any follow-ups, and then we go back up to these questions. Sorry for the spoilers, no worries. I will forget everything you said about Dragon's Egg anyway. I've just made a comment of Dragon's Egg. I'm going to stare at this later and not even remember that it's sci-fi. A while since I read it, but I think that was right. Yeah, but perhaps no spoilers. No spoilers if I'm going to read it, but as I said, I'll probably forget very quickly. Okay, so lots of comments here about Dragon's Egg, volumes of the universe. Let's go to this one. because this is follow-ups, and then we can move on to the other questions that were asked just now. Comment from Ben here. I saw there was also a follow-up to the Northern Lights. Come back to that in a sec as well. Comment from Ben, if the volume of the universe is infinite, is the amount of mass in the universe also infinite? So I want to say yes to that question, but that feels like a trick question, right? Because if we say that the mass is infinite, then there's going to be the follow-up of how was all of the mass created? But you need infinite energy to create infinite mass. So then it gets complicated, but if we assume we know how much mass there is in the observable universe, we have no reason to assume that our observable universe is privileged. So we can extrapolate, or we know kind of the density of particles in our universe. So we can kind of, in our observable universe, sorry, so we can kind of extrapolate that to the full universe. But if we're talking about an infinite size, we're talking about an infinite volume. And then when we're talking about the density of an object stretched over an infinite volume, that density also becomes infinite, or at least the mass becomes infinite. So yes, if we were talking about an infinite universe, we would also be talking about infinite mass. How do we create infinite mass with infinite energy? How do we have infinite energy? Infinite doesn't make sense. Yes, it's very I love this because it feels like a very straightforward question, but I feel like the answer to it is very, very difficult to conceptualize, very difficult to think about, because humans are not good at thinking about infinitely big things. So when we say the universe is infinitely big, what does that even mean? And how do we think about something that is literally everything? Yeah, so it is a very good thought pattern there. If the universe is infinitely big, it has infinite volume. If it has infinite volume and we know the density of things, then there must be infinite mass. That is a very correct reasoning. The problem is thinking about infinitely big things is something that basically breaks our brain, breaks our math as well. And it's something that is very difficult to think about. Which is also one of the reasons why we just say, yeah, infinite mass divided by infinite volume equals a density of 1. No, because you can't just say infinity divided by infinity is 1, because these infinities might have different sizes. And this is where mathematically you have to do the thing if you take the limit of the function and figure out what is happening in the limits. And if you ever encounter limits in mathematics, you know that it can be applied to the universe as well. So, yes, I think a universe with infinite volume and infinite mass will degenerate to having a uniform density with 0 entropy gradient. Would it? I mean, that might. Would it though? Thinking about infinitely big things breaks my brain, hurts my brain, breaks the math. Yes. If we're talking about an infinitely big universe, then it becomes quite hard to even define density, because what does density mean if you're averaging over an infinitely big space? Yeah. Which is also why one of the reasons why we only talk about our observable universe. Every claim we make, everything we say about dark matter, about dark energy, about the CMB, all of this is inside our observable universe, because that's the only part we can really talk about. Hey, Nina, great to see you. It's really the only part of the universe we can talk about is the observable universe. We assume that our observable universe is not a privileged place and that we can extrapolate what we see to the entire universe. But talking about the entire universe is something that is very difficult to do, because what does the entire universe even mean? How do you define something that has infinite volume? How do you define something that has infinite size? It's just something that is very difficult to mathematically or in any way think about, which is also why we usually limit ourselves to the observable universe, because that is the patch of the universe we can observe. And that is the patch of the universe we can actually make claims about. But I love these questions that the more you think about them, the more confusing it gets. So that is a very cool question. Sticking with the follow-ups, and then we'll go back to what I was saying here. So there was the follow-up by James here to add to the answer about the infinite, about the speed of light and the size of the observable universe. If universe was always infinite, is the Big Bang just an event in an existing universe? Yes, the Big Bang the Big Bang itself is not actually an event. It's the theory we use to describe the history of the universe. Now, if you want to think about this moment of inflation, That is something that happened everywhere in the universe at the same time. So the Big Bang is indeed an event that happens inside the universe. The Big Bang is not a theory of the origin of the universe, because that is something we cannot actually describe mathematically or scientifically, because inflation is this period of exponential expansion that we believe happened in the very, very, very early universe. And inflation erases the memory of anything that came before. So the earliest time we can talk about, cosmologically speaking, is inflation. And anything, we can talk about the seeds of inflation, what triggered inflation, but anything that came before inflation is lost to us. So there's often this thing that we talk about the end of inflation as being when we start our clocks. Inflation might have lasted billions of years. Then there's also the thing that there's this slight difference where some people say Big Bang when they mean the origin of the universe, and some people say Big Bang when they mean the end of inflation. And usually when we show these standard sketches of the history of the universe, you'll see there's this initial point that is Big Bang, and then there's cosmic inflation. And this is quite misleading, I think, because we cannot actually define anything that happened before inflation. So usually we talk about the Big Bang being the same as the end of inflation. And you might notice that I try to be careful when I'm talking about the age of the universe or when events happened. And I'll say things formed, like the CMB was formed 380,000 years after the end of inflation. And I try to use that instead of saying after the Big Bang, because the Big Bang is kind of a not properly defined point in time. But if you want to think about the Big Bang as being this period of cosmic inflation, then yes, this happened everywhere in the universe at the same time. So it is not in any way a theory of the origin of the universe. That is something that we actually can't answer, which is very cool. I think that the Big Bang is often, like, one of the criticisms of the Big Bang model is, oh, it doesn't explain the origin of the universe. Well, it never intended to. The Big Bang theory is not about the origin of the universe. It's about the evolution of the universe, how we go from that initial thing to today. And how we got that initial thing is not actually part of the Big Bang theory or the Big Bang model. So when some people say, like, oh, but where did the universe come from? We have no idea. What happened before inflation? We have no idea. So yes, the Big Bang or cosmic inflation is an event that happens inside an existing universe. Yes, it is not the origin of the universe. Okay. You said inflation erases the memory of everything that came before. Can you explain further? Yes, I can. And then I'll go back. I know there's other questions and follow-ups. There's more talk about eclipse. There was another question about the auroras, and there was another question unrelated to all of these. So we'll get to all of those. So inflation erases the memory of everything that came before. So the idea of inflation is that you take a very big, very dense universe and you stretch it. So inflation stretches space-time. We know that currently the universe is undergoing accelerated expansion, but imagine if this was happening exponentially. So this is the idea of inflation. You have a lot of energy, you have a lot of mass concentrated in the universe. This triggers, or something triggers, this inflation, where everything in the universe starts rushing away from everything else. Space-time is stretched dramatically in every direction. And it is stretched so much that once inflation has finished, it leaves behind a basically flat universe. And it is so dramatic that things during inflation, depending how long inflation lasted, everything could be pushed so far away that today it would be outside of the observable universe for us. So just going to draw a sketch here of what something might have looked like before inflation. And again, talking about before inflation is quite difficult. But imagine you have a blob. Here's our blob. This is a blob. Let's say this is a patch of the universe before inflation. And there are these 5 things inside. Not really going to call them particles, because at the time of inflation, there weren't even particles. But let's say there are things here. Quantum fluctuations, whatever you want to call these things. When the universe expands exponentially, these things get so far apart. I'm just trying to put them in the same place. So you can imagine that this is before and after inflation. So this might be before inflation, and this might be after inflation. But the size of the universe, or the amount of the universe that can send this information, so the size of the observable universe, doesn't grow as quickly. It still grows, but less quickly. So it might be that, just drawing another circle here, this was the observable universe before inflation. This is the observable universe after inflation. And you can see a lot of the things that were inside before are now outside of our observable universe, which is this oblong patch that I've drawn down here. So because inflation happens so dramatically, inflation can happen faster than the speed of light, because we're not talking about something moving through space-time, we're talking about space-time itself. So this means if inflation lasted a long time, everything that at some point was talking to each other is now so far away that it doesn't talk to each other, which means everything that is now outside of our observable universe, we have no access to. So whatever these particles were saying to each other before inflation, or whatever these things were doing before inflation, that is lost to us now, because this universe, the universe itself, or every patch of the universe has grown so much that the observable universe, it couldn't really keep up. So things were, the technical term here is that things were pushed beyond our causal horizon. So that means that during inflation, things get pushed so far away that they cannot send us information today. Later on, as the universe expands exponentially, more things re-enter our observable universe. But this is the idea of why we say that inflation deletes the memory of what came before, because in order to explain why the universe looks the way it does, why the photons in the cosmic microwave background radiation are approximately the same temperature always, there's these tiny differences, but these tiny differences are 1 part in 100,000. So how do we explain that the background temperature of the universe is like practically 2.73 degree Kelvin everywhere? And to do this, we need a certain amount of inflation. That means that everything has grown so much that everything we see today was in a place where it could talk to each other in the early universe, and then it could balance out temperatures. So we have a limit of, we need at least this amount of inflation. This number is given as 50 e-folds, which just means the universe needs to have undergone at least 50 exponential expansions. So e to the power of 50. So, hey, Aina, great to see you. I just realized we have Aina here. So nice to see you, Aina. It's great to have you here. Old friend, really nice to see you here. So, yeah, because just got completely distracted there. So in case people are not seeing that on YouTube, those are comments coming in on Twitch. So yes, because the patch, we know how much inflation there should have been in the early universe, then we know that a lot of what could have been inside a bubble talking to each other today might not be in the same bubble talking to each other now. So if it was talking to each other then, it might not be talking to each other now. So when I say inflation deleted the memory of everything that came before it, it's because a lot of stuff that could have been happening in the early universe before inflation is pushed so far away that we don't have access to it. So this is what I mean when I say it's beyond our reach. It's deleted what came before because it's just pushed it so far away that we might never be able to recover that information. So inflation happened at a speed faster than c? Yes. Because we're talking about an exponential growth of the universe, it could have happened faster than c. Now, there's a problem here about talking about the expansion of space-time happening faster than the speed of light, because when you're talking about speed, it's like with speed is always relative. So when you're talking about the expansion of space-time, it's quite hard to give it a speed, because it is something that you can't really say, like, with relation to what. The universe is expanding faster than the speed of light with relation to what, because speed is relative. So it's quite hard to define a speed for the entire expansion of the universe, but there could have been an expansion of the universe. There could have been expansion of the universe faster than the speed of light, because the limit of nothing can travel faster than light is nothing traveling in space-time can travel faster than light in a vacuum. However, there is no such restriction on space-time itself. So space-time itself can travel faster than light in a vacuum. So yes, inflation pushes everything so far away that it might be out of reach of everything we have today. So that's why I say that inflation deleted the memory of everything that came before. I heard someone use this phrasing in a seminar once, and I just love the phrasing, and that's why I reuse it, because I feel like it's very, very explanatory. It makes a lot of sense that then you think about things no longer being accessible to us. So I have seen now 2 questions about entanglement. I will get to the entanglement questions very soon. I know, Faisal, you've now asked me 2 things about entanglement. Going to get to that. Okay. Just going back, there were some comments about the monthly eclipses. I just want to very quickly answer the monthly eclipses one there. Where was it? Okay, I lost the monthly eclipses one. I'll go back to those. There was a follow-up by Prath on the whole discussion about northern lights. Is it possible to have an aurora where the photons emitted are outside the visible spectrum, like microwaves or X-rays? Let's hope the sun does not send us gamma rays, because those would be dangerous. Now, the photons themselves don't need to be within the visible spectrum when they're emitted from. So the northern lights is not so much about the photons being emitted, but rather the charged particles that are emitted from the sun that then get caught up in our atmosphere. So the sun has solar wind and solar flares. There's kind of 2 things that are emitted from the sun when you have a solar flare. One are the photons, the particles of light, and one are the charged particles. And the charged particles are the ones that then get caught up in the atmosphere, and as they travel through the magnetic field, they produce the photons that we see in the northern lights. So I'm not sure if your question there is that the photons produced in the atmosphere would be outside the spectrum that we can see. That can happen. As for the ones produced in the sun will produce them across the spectrum, depending what it's doing. And those are not the ones that, so the photons emitted by the sun are not the ones that produce the northern lights. The ones that produce the northern lights are actually the charged particles the sun is emitting, which get caught up in the magnetic fields. Okay, and going back to the questions that I just wanted to answer about the eclipses, where we were talking about the possibility of monthly eclipses, and Scott said, do you think it would be boring if we got eclipses every month? I think it would still be very cool. And then there was a follow-up from David Howden. I wonder if a monthly eclipse cycle would have made working out that the moon orbits the Earth and then the sun happen earlier. Yes, if we had monthly eclipses, I think it would have been easier to figure out what rotates around what, because during eclipses is when you really get a lot of insight into what objects are rotating around what other objects. Okay, just did some quick fire questions. I want to come back to the entanglement ones. Let me just check the follow-ups. Gamma rays would not turn us all into the Incredible Hulk. Gamma rays are actually pretty dangerous and pretty damaging. It's good that we don't have a beam of gamma rays pointed directly at us. So we don't know what caused inflation in the first place, and figuring that out is a big deal. Yes, because it's very hard to figure out what could trigger inflation. There are some ideas of could inflation have been triggered when the forces broke away, when the electromagnetic and the weak force separated? Did that trigger inflation, or did inflation trigger the separation of the forces? Why was there inflation? There are people trying to figure out the initial conditions, or like what triggered inflation. And one cool thing that we can do is, depending on how long inflation lasted, it would have left a specific, because this is dramatic expansion. You can imagine if the universe is growing so much, there might be stretch marks in the universe in the form of gravitational waves. And if we could measure the gravitational waves produced by inflation itself, we could answer a lot of questions about what inflation looked like. We haven't been able to measure these yet, and the fact that we haven't been able to measure them allows us to put limits on what inflation could have been like, because the fact that we can say, okay, we haven't seen gravitational waves means inflation couldn't have been incredibly big or incredibly small. You know, there's some ideas of the shape of the field that triggered the inflation, and we can limit this based on the fact that we haven't yet found these gravitational waves coming from inflation. But it's easier to rule things out than to rule it in. As to what caused inflation to stop, you can kind of think about, that's something that we think we might know. And one thing that we often think about, running out of place to sketch, need a new piece of paper here. One thing that we often think about is inflation slowly rolling down a hill. So we call this like slow roll. So if you imagine this is the potential energy that caused inflation, there's a ball slowly rolling down and down and down. Once it starts rolling down, the universe expands, and when it reaches the bottom, it kind of runs out of energy. And this is when inflation would stop. So we can talk about inflation ending, basically when the field that triggered inflation ran out of energy. As to what caused inflation, that is a big question. And how long did inflation last? That is also the big question. But yes, these are things that are very difficult to answer because we're talking about stuff that happened in the really, really, really universe, and that now might be so far away from us that we don't have access to them. So yes, if we could figure out any of these questions about inflation, it would be extremely cool. Okay, so there was two questions now by Faisal about entanglement, and I want to go back and try to find the first one, and then I'll answer the second one. I see they are actually very related. So the first question was, are all the particles in the universe entangled? And the second question, let's go back to the second question here. Are the particles entangled with each other because they interacted before inflation? Yes, so very related questions here. Okay, sorry, just going to clarify because I didn't label my axis on. Now there's a question about the axis on my graph here. So let me just put here that this is what we call phi, which is not going to help, and this is v of phi, which is also not going to help. This is the potential of the field phi, and this is the field phi that is rolling down this potential. So what does the bottom of the graph mean, and why is it there? Why not a lower or higher limit? I mean, it doesn't necessarily have to be 0. You could just have something like this. So if you have a potential rolling down here, once it reaches here, it kind of runs out, it reaches a minimum, and then the field itself doesn't have more energy to give. So the lower limits here that I first drew is just like the lower limit of the potential energy of the field that drove inflation. I know this sounds very math heavy and jargon heavy. So when I'm talking about a field, I mean something that has a value everywhere in space-time. So if we consider velocity is associated to an object. My pen has a velocity. If I move on my chair, I have a velocity. It's a specific thing. But then if I talk about the temperature, it's something you could measure anywhere in the room, right? You could take a temperature measurement here, 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 here. Therefore, you can imagine the temperature to be like a field where you can take its value anywhere. It's something that is everywhere in the universe. So a field is something that is everywhere in the universe. When we talk about forces, we can talk about their associated fields. The electromagnetic force has an associated electromagnetic field. When we're talking about the field that triggered inflation, the idea here is there could be some particle that we're calling the inflaton. This particle has a field associated to it, quite like how photons can have the electromagnetic field associated with them. And this field, this inflaton field, is what could trigger inflation. So when I'm talking about this potential energy, it's how much energy this field has in the universe. And once this energy is depleted, so to speak, then inflation stops. So we have a pretty good idea of how inflation ended, but how it started, what started it, how long it lasted, those are much harder questions to answer. You always label your axis. Some are better for wood, some are more for armed combat. Yeah, I think everyone should have like an array of axes. They're a very good thing to have lying around. Okay, entanglement. The idea of entanglement is that you can have particles that share very similar properties, but are slightly opposite. So the typical experiment that I like to think of is, imagine you have two rabbits. Or I take two, let's go with cats this time. You take two cats. One is the sweetest little angel cat that is lovely and very sweet. And the other is the absolute demon cat that will scratch you and bite you the second you get close to it. Now, imagine I have these two cats. I have the super nice cat and I have the utterly evil cat. I put both of these cats in boxes, physicist cats, boxes, match made in heaven. So I put my cats in boxes and I send them to different places. Because nobody saw which cat I put in which box, you could say that these cats are entangled. For sure, one of them is good and the other one is evil. If you get a box with a cat, you don't know if the cat is evil or good. So the moment you have that box in front of you, the cat is both evil and good. This is Schrodinger's cat, the thought experiment with Schrodinger's cat. However, once you open the box, you know for sure if you have the sweet little angel cat or if that cat has attacked you. You know this. Once you've opened the box, you know if it's a good cat or the bad cat. And once you've opened that box, you don't need to open the other box. You know for sure which cat is in the other box because you have the good one, the other one has to be evil. So you could say that these cats are entangled. One is good, one is bad. These are cats that, this is something that was set up in the way where you have a good cat, you have a bad cat. Now, this analogy is going to break down because cats are big objects, whereas entanglement happens on the quantum level, and then there's the whole idea of quantum uncertainty. Because with the cats, there's the thing that it was already determined from the beginning which was good and which was evil because I put them in the box. But in a true quantum state, if you do that experiment without measuring which is good and bad, there is no, not even I would know, the person who put the cat in the box, I wouldn't know which is good and which is bad. So there is this level of uncertainty in quantum physics that makes entanglement possible. However, there's no reason to assume that every particle in the universe is created with an entangled pair. You can create entangled particles under specific circumstances. For example, if you have magnetic fields aligned in specific ways and you send electrons through, and you know the ones that go one place and ones that go the other, you can create this entangled thing. Even the nice cat probably won't like being packed up and shipped. Yeah, although cats like boxes, right? So maybe the cat will be happy. Anyway, please do not ship your cats. Put cats in boxes. Don't ship your cats. But yes, you can have particles in the universe that are entangled, where if you measure one, you know what the other one is in. You can have I have to put this joke on screen because this is an extremely funny joke here. Cats may be too big for entanglement, but what about cations? Cations are also too big for entanglement, but I love that. I love that. Yes. So can photons have entangled partners? Well, when you're doing entanglement, so let me just finish the trail of thought that I had. When you entangle particles, you can set them up so that you have one doing one thing, one doing another. But there's no reason to assume that every particle in the universe has an entangled pair. And even if it did, unless you're setting it up, if I measure something in the universe today randomly, I don't know if it's entangled with some other particle somewhere else in the universe. So even if everything in the universe were entangled before inflation, it doesn't really allow us to gain more information now because these entangled states we don't know what they're entangled with or what property was entangled. Because you can have particles that are entangled in one property, but not necessarily in all of them. So, for an example, if you prepare electrons that have spin up or spin down, then you can put them, one is spin up, one is spin down, and this is something you can measure. But then if you measure spin along a different direction, you've entangled the up down direction, and then if you measure spin left right, they're no longer entangled, right? So entanglement is you entangle specific properties of pairs of electrons. So short answer there, entanglement is weird. There can be entangled particles, but not everything in the universe has to be entangled. So how will you know that the other person has the bad cat for sure faster than light? Because I know for sure that I have the good cat. There's one good cat, there's one bad cat. So if I open my box, you don't have to call the other person and say, hey, I got the good cat. I know for sure that because I have the good cat, the other person has the bad cat. This is not information traveling faster than light. The information is contained in the system. As soon as one of the elements of the entangled pair is measured, you know the state of both. So, I have fruit fly. So entanglement is a very cool thing. It's a very useful thing. And it's something that is very confusing. This fly is going to annoy me. I got new plants in the house, and new plants mean I have tiny fruit flies, and these tiny fruit flies are bothering me. So yeah, how do I know for sure that the other person has the bad cat? Because they have the good cat. Entanglement is weird. You can have particles entangled across different properties. If you measure one, you know the state of the other. Can photons have entangled particles? What are you trying to entangle with a photon? Because usually when you do an entanglement, if you prepare an entangled system, there's a specific property that is entangled, and that is usually flipping one of the quantum numbers. We use a case of electrons where you can have spin up and spin down. Photon doesn't have charge, a photon doesn't have spin. Photon doesn't have an antiparticle. So trying to make a pair of entangled photons, currently I would say no. I might be forgetting something, but I would say no to entangled photons, just because which quantum property are you flipping? And that is the problem there. So yes, entanglement is weird. We don't know if particles were entangled in the early universe. There probably were pairs of entangled particles, but that doesn't really help us to measure things because we don't know what is entangled with what and what property we need to measure to get the entanglement to happen. Incidentally, or like not incidentally, off topic, if you want to practice about with some of the fun ideas of quantum physics, there is a version of the typical tic-tac-toe that is called quantum tic-tac-toe, and it's the same idea where you have x's and circles and you need to get three in a row, but you entangle the playing game, the board. So every time you actually do like two moves, but they're entangled, and one and the other have, you can collapse one. So it's very fun, and we actually played it. Last September, I was the teaching assistant on the quantum mechanics course, quantum physics, or introduction to quantum physics. I just hesitated because it was like September. It was a long time ago. No, it was November and December. Yes, which is still a long time ago. But on one of the first weeks with the students, we played quantum tic tac toe, and it was super fun. Okay, if particle A is entangled with particle B, can I still entangle A with particle C? Yes, but you would kind of break the entanglement with particle B. Or it depends what properties you're entangling. Can you have a three-state entangled system? So I think you'd have to prepare it in a way where you entangle all three at the same time. But if two are already entangled and then you try to entangle a third, when you set it up to entangle to couple this third one in, you have to do some type of measurement. So then you break the entanglement in the first two. So then it will kind of flip into that. So yes, if you try to add a third one into the mix, you change the entanglement, but you can prepare them in a state where you already entangle A, B, and C if you have enough properties to entangle. But yes, entanglement is weird and funky, and cosmic inflation is weird and funky. And I love that we're talking about both of those things because they're both very weird topics. Okay, time for a quick comment recap because I might have got through all the questions now, but I might have missed one. So let's just very quickly take it all from the top again to make sure I got through all of your questions. You still have 2 or 3 minutes left if you have a burning question that you need to ask. And if you think I missed your question, now is also a good time to ask it again, just in case I miss it in my quick recap here. I'm just glancing through, but I think there's been over 100 comments today. So just very quickly, glancing through, we had comments about the big red spot. We talked about northern lights quite a lot. We talked about eclipses. That was a fun tangent. We talked about the colors of northern lights. Okay, then there was that question there. Okay, yes, I knew I'd overlooked a question from James. Nearly 45 minutes ago. I would like to know pictures of planets as seen from naked eye. If you were flying by in a spaceship with all these images, we lose the reality. I'm not completely sure I understand your question there, but of course, any image we take of a planet is never going to be completely realistic. A lot of the space images you see, like from the Hubble Space Telescope or JWST, are color corrected. So the color that we see them in is not like the true color, but it's color corrected based on the camera, based on the wavelength at which the measurement is done. So a lot of space photos do not depict the true color that you would see that object in if you were close by. But yes, it is usually this color correction is like scientifically based. It's not completely random. But yes, also, when we look at the CMB, the photons are actually not orange and blue. They are temperature differences that we depict as orange and blue. And yeah, I think that's now the 5th appearance of the CMB today. So yes, the images we get of different planets are not necessarily completely realistic, but they're good approximations of what we would see, or at least we try to make them to be good approximations. I had in mind that there was one question that I had missed, so that I'm glad I got to that one. Okay, more questions. There was a tangent about Doctor Who that was always nice. Question from press that I think David Dunn immediately answered. Is it Uranus or Neptune with the 98-degree tilt, the one that's basically on its side? This was when I was talking about the planes of rotation of the different objects. One of the planets in the solar system is on its side. And yes, that is indeed Uranus. It is 98-degree tilt. So if this is the plane of the sun and the Earth, Uranus rotates on that plane, and I am deliberately mispronouncing that, yes, because there are too many jokes if I pronounce it properly. Yes, you're simultaneously envious and pitiful of those who live where the aurora is an ordinary occurrence. Yeah, I see that was a different conversation there, but yes, it's I think Northern Lights are very fun, and we covered that it would be very cool if we could see them all the time. CMB looks like a star. Sure, CMB looks amazing. Uranus also has some gazing effects. Yes, so yeah, it's a weird planet. There are more comments about Dragon's Egg. Yes, I have a comment written down that I need to watch Dragon's Egg. Then we got into the size of the universe, the size of the observable universe, what it means to have infinite mass, what it means to have infinite size. These were very fun and confusing questions. Okay, let me see. I think I answered all of those questions. Yes. Okay, yeah, here towards the end where we had we're figuring out what caused inflation would be a big deal if we can ever figure that out. I know I'm just doing a quick recap here. I'm just checking that I got through all of the questions, and I think I did. Okay, we talked about entanglement. Entanglement is weird. There's a comment here. So is the information encoded at the point where the cats are separated? Yes. Not the point where they're separated, but the point where we establish that we have one very good cat and one very evil cat. In the quantum world, you'd prepare it such that these are two entangled particles or entangled cats. And the moment you prepare them is when the information is encoded in both sides. Then, because it's quantum nature, both of them are simultaneously good and bad until you measure one, but as soon as you measure one, you know for sure what the other one is doing as well, because they were prepared this way. So in the idea of a truly quantum system is that until you open the box and ask whether it's a good cat or a bad cat, it is both. Both cats are good and bad. There is no way of distinguishing which is which. Then the universe rolls a dice and decides which is which. But the moment you measure one, you know the other one as well. Okay, let's see. A few last minute questions just came in here. One from Karma here. Time for my weekly question to the expert. Glad you consider this a weekly thing. This is the idea, weekly Q&A with a physicist cosmologist. Have you ever heard of the cosmological scale asymmetry in galaxy rotation directions? Vaguely, yes. Cosmological scale asymmetry in galaxy rotation directions. I think that this is the thing that a lot of galaxies seem to be right-handed instead of, like, there's no reason why galaxies should spin one way or another. And I think most galaxies seem to spin in one direction rather than the other. Like, there's not 50-50. But I'd have to check that out and read up on that more carefully, because right now I'm not completely sure. But that sounds like a cool thing. I'm adding that to my list of things. See, there's also the problem that I start writing down questions that you ask, and then I forget halfway through and get distracted. And under my list of open questions right now, there's just the comment color. Now, I'm pretty sure that was about color of northern lights and atmospheres, but for now, it just says color. And then I'll look at this in a few days and be like, wait, what was I supposed to look up about color? But the thing I was just writing around is galaxy asymmetry rotation. Yes, there's a fun thing to look up and then completely forget about. Okay, he claims to have found evidence for the rotation distribution to be opposite if you look opposite ways in the sky. Okay, that I haven't heard. So that I will have to look up. But yes, that sounds like a very cool thing. That's added to my piece of paper that now is covered in sketches as well. Comment from Prath here. You've had a burning question for a few weeks now. Great. How is time considered a scalar and not a vector? Dice time has a direction, even though we are locked in one direction. Do we even consider time to be a scalar? I mean, time is a dimension, so scalar is something that doesn't have an associated direction. For an example, if I want to measure the mass of an object, that is one number. It doesn't matter which way it's going, the mass is a mass. But for an example, if you want to measure the velocity, the direction, it has direction. You're either going this way or that way. It's something that implies a motion, so implies a direction. So then we'd say that the velocity is a vector because it has multiple components, whereas a scalar is something that only has one component. So why do we consider time to be one? Well, technically, time is part of the four-dimensional vector that is space and time. So time is one of the 4 points that we give there because it helps us determine location. But then I guess the question there is, why do we consider time to be one thing? Now, even if we consider that there's an arrow of time, which there seems to be, so yes, maybe color was regarding. No, I'm pretty sure the color comment here was not about the color of planets, but was about the color of atmospheres and northern lights, because I think that's the one I was writing down. Yes. The thing I was just answering, if even if you consider time to be a line, it still only has like two possible ways, right? You could either go back in time or forward in time. So this would basically be a minus sign, but it's still one possible thing. If you want to go back in time, then you say minus t. If you want to go forward in time, you say plus t. Whereas if you think about using the thing I was just saying of time and space being a four-dimensional vector, you have the three of them that you called the space ones. You're also giving like one number to x, one number to y, one number to z. So in out is one, up down is one, and left right is one. So then forward and back in time is also one. So they are components of space time. But even if you consider the idea that time could go forward or backwards, it's still linear. It's not something that you can go up, down, left, right, around. You can fully specify it with one number. Even if you want to revert it, you just put a negative in front of it, assuming time here is one-dimensional, which is the current assumption. I know there was a question at some point on the stream of what would happen if time was two-dimensional, and I asked people at work, and everyone was like, don't make me rederive math. Don't make me rederive all of physics. No, time is one-dimensional, leave me alone. So that was the general consensus of like, Follow up here. What if mass was a vector? If it measures one value in one dimension, but another in another dimension? That would be interesting. What would another dimension of mass look like? Where would this dimension hide? What would that even mean? Very fun questions. Messing with dimensions messes with everything. But yes, it is very cool to think about what happens if you take things that are scalars or one-dimensional and try to make them multi-dimensional. And then you have to rederive a lot of things. So it's fun. It's much easier to do the other thing and take something that is three-dimensional and just focus on one dimension, one direction, then you forget the rest. But it's doing dimensional reduction, reducing the number of dimensions is easier than adding the number of dimensions. Yeah, you only asked about multi-dimensional time. Yes, generally multi-dimensional time, the consensus was we need to rederive general relativity. We need to rederive classical mechanics, go away. People didn't seem to like the idea of two-dimensional time other than so yes, it's very fun. It's one of those things that physicists are like that's interesting. But yes, very cool question. Follow up there that from Pratha, you say can wait for the next stream. That is good because I am already 10 minutes over today. But there was this comment here. You want to know my thoughts about the rotating Mercury telescope? Huh. Rotating Mercury telescope. What is that? I've never heard of that. That is also going on the list. Rotating Mercury telescope. That sounds fun. I don't know what that is. So my thoughts currently are I have no idea. I need to read up on that. But that is cool. I love it when you ask me questions that I have no idea what do you mean, because then I have to do my homework, which honestly I don't do. I'm terrible at homework, but I will try to look up some of the things that I've written today. Probably I'm going to look up Dragon's Egg and nothing else, but I have like 4 things on my list of things to look up today. And I know I still owe 2 or 3 of you emails. That is also on my mind. Thank you again to everyone who takes time to send me emails. I really do appreciate it. I promise I read them. I just don't get around to answering, and the last week has been so busy. Okay, we are 10 minutes over. There were a lot of very, very cool questions, so we went a bit over time today. But it's fun. I love it when we go over time because of all the cool questions, and there were some really fun questions today. So, quick announcement. I am not sure if there will be a Cup of Cosmology next weekend. If there is, it will be on Saturday instead of Sunday. So Sunday next week, I'm celebrating a friend's birthday. So I will not be doing a stream next Sunday. I might bring it forward to the Saturday. I'm not yet sure because I might have another event on Saturday. I'm doing so many things right now. Yes, the next couple of weeks, the streams are going to be a bit intermittent because I start traveling and going to conferences and organizing events. So yes, maybe next week instead of an AMA, we do a question catch up. Yeah. See, there's these four on the list. There's also like six in my inbox waiting for me, 6 or 7 questions in my inbox, which I've said before. I don't necessarily answer questions by email, but I do have the list. So yeah, there is a backlog of questions that people have asked me other weeks that are, I could go back through my notes and find the random questions. There's just like glancing through, I see something about Einstein-Rosen bridges, something about superconductors, oh, wait, I just found something. I gave a talk 2 days ago, and I was missing the notes that I made for a similar talk I gave months ago. And I just found the notes I made months ago that I would have needed 2 days ago. See, this notebook, things get written here and then never looked at again. Yes. I should figure out what is in that notebook. Also, I did not know this notebook was that old. Anyway, random tangent there. I see my notebooks are chaos unto themselves. But yes, next Sunday, they are. Yeah, I think raising multidimensional time is the proudest moment of your life. Yeah, multidimensional time is something that was a very fun question and bugged us a lot. So well done. That was a cool question. Yes, as I was saying, next Sunday, there won't be a cup of cosmology, depending on how my busy week goes or how busy my week is. I might do a stream on Saturday, but it's still not a guarantee. But then I should be back online in 2 weeks, and then I'll be off again because I'm traveling. Then I'll be back. Then I'll be off again because of my own party, and then I'll be back. So next few weeks are going to be a bit intermittent, but next Sunday there won't be a live stream. I will try to do one on Saturday, but I currently cannot guarantee it. So for sure, a Cup of Cosmology will be back online in 2 weeks, same time as always. That's 8 p.m. in Helsinki time, 7 p.m. in Europe, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. As always, there is a time zone converter on cupofcosmology.com where you can figure out when the next stream is in your own time zone. Also, there are some changes to the webpage if you feel like poking about. There are some changes to the Cup of Cosmology webpage. I did a bit of maintenance the other day. Nothing dramatic. There's just a few things that have moved. You're welcome to go find what's moved if you're so inclined. But yes, this has been great fun. Thank you everyone for joining. Thank you for the very cool questions. Been super fun. Cup of Cosmology will be back again at the latest in 2 weeks, maybe with a bonus one next Saturday or a shifted one next Saturday. I hope to see you all in the next stream. And I hope in the meantime, you all stay safe and take care of each other.